Alright, welcome back ladies and gentlemen. Now we're going to do some kinematic and dynamic analysis. Before I do though, let me show you a little thing that you need to do before you do dynamic analysis. Before even I do that, let me just explain what kinematic and dynamic analysis is. Kinematic analysis allows you to kind of calculate position, velocity, and acceleration. So if you think back to physics, it essentially solves kinematic equations for you. But then the dynamic analysis gives you force values. And it gives you reaction forces in all these pin connections we made. Because if you think about it, this link rotating about this shaft, it's going to have some sort of reaction, some sort of dynamic load on the shaft. Because it has a torque applied to it, and that has to have some kind of load on it, right? It should make sense physically. If you have engineering background, you should understand what that means. And I'm not gonna try to teach you physics now. But that's what dynamic analysis lets us calculate, and it gives us values for that. Now, we can open up these parts right here. Again, these parts are what makes these assemblies. We make them separately, but we can right click and open. When you do that, it opens that part in a separate window of its own. It opens up a Creo parametric window. We're not in Creo parametric assembly environment anymore. We're in parametric modeling environment. And what we can do here is we can we can click File, Prepare, Model Properties, and right here in Material, you should have some sort of material selected. I have steel. You can assign it by hitting change and say steel, and then click this arrow that points in the direction, the right direction, literally. Okay, so once you do that, you should have a material here with the red arrow pointed out to it. If you just have a material and there's no red arrow pointed to it, right click it and say assign, like this. So right now there's no red arrow pointing to the steel. That means it's not assigned. If I right click it and say assign, now it's assigned. And then I hit OK. And then I close it, and I already have this as IPS, so make sure yours is IPS as well, inch pound second. I'm gonna hit save, I'm gonna hit OK, and then I'm gonna close it with this feature again. And do that to all of your components, because if it isn't, dynamic analysis is not going to work. You can still do kinematic analysis on your components without material properties, but you need material properties to assign to do dynamic analysis. And another thing I should mention about material properties, I wonder if I can through here. Let me go here. Okay, so when you open up these material properties, you'll notice that there's just 15 or 20 of them. And if you want to have more materials in here, you can make your own set of material properties. And the way you do that is you click Create New Material, and then it pops this window right here, Material Definition. You should know what these values mean: Young's modulus, damping, thermal expansion coefficient, tensile stress, ultimate stress. These are all engineering terms. You should understand what they mean. They're not engineering specific terms, but you should know what they mean. And you can select the type of materials, and you can define thermal properties, appearance, and all that fun stuff. And the density is an important one. So you can look these things up online and make your own materials, and then you can save them in a flash drive in a folder of your own, where you can have your own material library, which is what I like to do, because you don't want to keep reassigning materials and keep saving them. You want to have it all saved in one folder, and have a convenient spot to just look at and look up the MTL files. So you're gonna save them as .mtl files. Alright, so that's that. That's how you do material properties. Now, to begin kinematic analysis, we need to go into the mechanism environment. And the way you do that is you click Application, then you click Mechanism. And this is the environment we're going to use to do any kind of kinematic or dynamic analysis. So any analysis that involves moving parts, you do that in Creo Mechanism. There's more areas where you can do things, but this is the first place you come to if you want to do any analysis that involves moving parts. And from this, you should be going to finite element analysis. unless somehow you already have force values for it or load values for it, which I don't know how you would get those, but this is the first step. So here we get to do things like assign motors virtually. And what I mean by that is you can select an axis and say that we want to apply a motor, a motion, applied motion there. So the way you do that is you just click a servo motor, and then you select an axis right here. It says pick an axis. Select the axis, and it shows you which link it's gonna rotate or which component it's gonna rotate, and it shows you the direction of the torque and all that stuff. And then you go to profile, and then you can select velocity, and the units are degrees per second, and I'm gonna say 360 degrees per second. That means it's gonna go around once in 1 second. It's very simple and very straightforward. Um, and then we can do our analysis. So this is enough right now to do a kinematic analysis, and I'm going to do that, kinematic and dynamic actually. So the way you set up an analysis is, I should actually differentiate. What we did now is put in a component in our mechanism that's gonna affect the behavior, but we haven't actually set up our analysis yet. The way you set up your analysis is you can either go to this analysis tab right here, click on mechanism analysis, do playback and all that stuff, and have your windows open. I like to do it through this mechanism tree though. It's I think it's more convenient because you have everything right here. You can mess around with more things like motors, springs, dampers, which we'll go over later on. But just keep in mind that you have a lot more available to you right here versus there. Then again, you can do what you like, but I'm gonna start an analysis using this option right here, analysis. If you look at the icon, it's the same icon, mechanism analysis. I'm going to right click and I'm going to say new. When I do that, it opens up this analysis definition window. This is where we set up our analysis. So instead of position, I'm going to say it's kinematic. Motor is already selected. That's the motor that we applied here. Remember, it's a component. And then we have our setup. Now, frame rate. That's kind of what you use to control how well do you want to analyze. I'm trying to find the right words here, but this is what controls the precision, if you will. But let me just do two separate analyses. So let me just leave it the way it is now with 10 frame rate and end time is 10, and I'm gonna just run this analysis. So look at this, and it's done. And once you hit done, under playback, you're gonna have your analysis saved. Another I guess terminology I should explain. You can set up your analysis right here, but once it's done analyzing, it's gonna save all those calculations it did under playbacks. So everything that you analyzed and every calculation that was done, it's saved in this little playback section right here. And then I can go to measure. So playbacks are saved, and they're what supplement measures. What is a measure? So everything that we calculate, we can display it. We have to have some way to display it, and that's what the measure tool allows us to do. So we can see right here, analysis definition from the playback, we have that as something to supplement our measurements. How do we measure something now? We click new, and then watch, it gives me this window right here, measure definition. Now the type, this is where you can select different type of things you want to measure. Let's say I want to measure the velocity. I select velocity, then it's asking me where do you want to measure the velocity. I can select a point or a motion and axis. And I want you to understand what that means. A motion of axis is pretty straightforward. You can select a motion or axis, but the point is where the most of the power comes in. So you can have this part open up in a separate window, in a parametric modeling window, and you can place a datum point anywhere, and then you can select that point as your point of measure. I'm gonna select this tangent point right here because that's an automatically made one, but I don't want to go back and make a point. So I'm gonna just select a tangent, and I'm gonna say apply. Okay. So we have some numbers next to our measure now, right? right here. If we make this window a little bigger, we have some measures. We can graph this right here, click this graph, and we can display exactly how the velocity is. And it's exactly what we expected, because we applied a constant velocity, and it is a constant velocity. Acceleration, if we try to display it now, if we edit this measure right here, by the way, we can edit the measures. We can edit it, and we can say, show me the acceleration at the same point. So I'm gonna leave it as the same point. I'm gonna hit apply. I'm gonna hit OK. Let's look at this. Acceleration is I guess, wow, there's an acceleration. There shouldn't be an acceleration. It should be a constant velocity. But then again, the acceleration isn't changing. Interesting. What is the acceleration? Let me look at the value. Well, whatever, I guess. I don't really care much. But let's look at that's the acceleration. Apply. Okay. Here's what I was doing wrong. So it matters where you measure things. Of course, that link is gonna have some acceleration, but we applied the motor at a particular axis, and if we measure the acceleration there, it's 0. I was doing something stupid there. So let me edit this. When you measure the acceleration at points that are moving, relative to the motor, obviously we're gonna have some acceleration, and that makes sense. But if you measure the axes, there should be 0 acceleration, which it is, and it makes sense. Everything's okay now. I was worried there for a second. I'm like, what's going on over here? Okay, so that's kinematic analysis. But now let's try to measure, and let me go into edit again, and let me measure connection reactions. And now it's asking me to select an axis again, and I'm going to select this connection reaction right here, and it's going to show me the connection reactions. I'm going to apply, hit OK, and watch. It's saying not computed because we didn't do dynamic analysis. And when we do dynamic analysis, we have access to everything that we did with the kinematic analysis and the force values. And the reason I want to differentiate this is because if you have large assemblies, dynamic analysis is going to run much slower. So if you don't need the force values, you only need to analyze the acceleration and velocity for things, for mechanisms, do kinematic analysis because it runs much faster, than dynamic analysis. But before I even go into dynamic analysis, let me go right here again. Under analysis, I have analysis definition already set up, but I'm gonna edit that. And if you remember, I was talking about the frame rates, and let me go back to the measure tool again. This is so all over the place. Oh my god. So let me go back to velocity. Let me go back to this point. Let me select this point again. Hit OK. Select this edit definition. Okay. So I want you to kind of look at this, or if I can make this point clear with the position measure instead. Okay, that's fine. Let's apply this. Okay, so that's the position. I want you to look at the gap between these circles. This is what represents at the point at which a measurement is taken. So every time you see the circle, there's a new measurement happening, and in between, Creo is guessing. It's just trying to connect the dots. That's crucial to understand, because now if we change the concentration of these little dots, these iterations at which Creo takes measurements, we can kind of improve the credibility, or I guess the accuracy of our analysis, right? But let me make that a bit more clear by applying an acceleration instead of a velocity. So if you remember, I applied a motor here with a 360 degrees per second of velocity. Now I'm gonna modify that right here under motors. This is why I like to work with the mechanism tree, because it allows me to just do things very quickly. I'm gonna go here, I'm gonna select servo motors, and then I'm gonna right click this, edit definition, go to the profile. Now instead of velocity, I'm gonna say apply an acceleration, and I'm gonna just say 360. You can set up an initial velocity if you like, but I'm gonna say it's 0. And I'm gonna say it has an acceleration of 360 degrees per second. Remember, it's acceleration, not velocity. The acceleration is going to remain the same, and I'm going to apply it. I'm going to hit OK. Now I'm going to run the kinematic analysis again. So watch. We have this edit definition. We have this edit definition option. We can just go back, but this time I'm going to run this for 100 frames, and I'm going to run this. Now, if you notice this, you should have noticed this immediately. This is much slower, and the reason is because we have acceleration applied now. We have things constantly changing, but moreover, we have 100 frame rate. That's a far higher number of iterations at which Creo's taking measurements and calculating things. So this time we should have those circles in our graphs far closer to each other. I'm gonna hit OK, and now I'm gonna go to measure again. We still have the same measure at the same exact point, but when we try to display a graph, watch. Look at this. The circles are so close together, they're almost merging. That should kind of tell you that, you know, this is how you get high fidelity. I'm zooming in right now, I guess. Let me zoom out. Zoom in. Wow, there's only a zoom in option. I can't zoom out. Isn't that fantastic? Okay, so I'm just displaying this again. Let me zoom in just enough to kind of show you. Okay, so if you look at the axes right here, x-axis, we're only looking at a certain interval of time, not the entire 10 seconds, and it's much closer together. This looks more like what it was for an entire 10-second span, which is something we have only in one second, which makes sense because we increase the frame rate by 10 times. So that fidelity makes sense. But let's look at, instead of position, let's look at the velocity. At the same point, we hit OK, and we measure it. There we go. The velocity is going up. We expect that because we applied an acceleration. Now let's look at the acceleration itself. It should have gone up as well. Okay. It goes up tremendously. It's 18,000 inches per second is something pretty fast. Okay. So here's something to note here, I guess. Let me select position again. Now, here's a little subtle thing. You can select your own coordinate systems. So this is an important feature because you can select the coordinate system with respect to which you want your measurement to take place. So this is not as important in forces, but it matters quite a lot when you're worried about position. So if you want to find the position of something moving with respect to a certain surface, let's say, you can make a new coordinate system and measure things there. So let me do that. So see right here under datum, we can make an option called coordinate system, and I'm going to make a coordinate system right here. I'm going to say that's my coordinate system, and it's, let's see, let me just make a reference 0 0 and 0. Okay, so I made a new coordinate system. When we enable coordinate systems, it shows us the coordinate system we made. It shows us a bunch of others as well, but I'm going to use this to kind of re-display my measure value for my position. And I want you to observe how it changes. Let me just edit this. Right now the coordinate system selected is, let's say, this one. I'm going to select it, I'm going to apply it, I'm going to hit OK. And I need to run the analysis. Nope, no I don't. Let me go back to the measure. There we go. So that's how this is. Let me change it to position. I'm sorry. Okay. So this is the position. It's 6 something. That's how far away it is, and that's fine. Now I'm gonna edit this, and I'm gonna change the coordinate system, and I'm gonna select this one. Watch, I'm able to select the coordinate system that I made. I hit apply, I hit OK, and immediately the value changed. So with respect to this system, we can see the actual motion of things. Now let me just get a little nicer angle right here. So if you look at this, this is actually showing us how it's moving with respect to that new coordinate system we made. And you can do this because Creo itself makes a bunch of automated coordinate system, but you can have your own coordinate system, one set in stone that you can use to measure other things. And it's that's just something I like to do because it helps me understand where things are physically. Here's another cool little feature, I guess, to properly display the power of this. So I closed down the measure window and I kept the graph open. Now, under playbacks, if you right click it and you hit play, you get this animation window right here. And then I hit play again, and you can kind of replay the whole animation. And if you notice, it's moving the entire mechanism. And as it's doing that, it's tracking the graph and the curves. And it's tracking exactly where we are physically with respect to that coordinate system, and it's showing us in real time. So this is a good tool to kind of visually display how things are working out. It's kind of slow, and I can speed this up. And there we go. I've sped it up now, and it's gonna go a little faster. But I'm just trying to show you the visual tools that you have available to you in Creo, and this is just kinematic analysis. And you can have this animation like this, and you can use it to kind of display how motion's working in an assembly, or how assembly works physically. So I'm going to close that, and now we're going to do dynamic analysis. So at this point you should be familiar with kinematic analysis, and I think I've shown you almost enough to do your own stuff. But let's do dynamic. So I'm going to right click this again. I want to try to, without sounding too redundant, I want you to understand that you add in a motor as a component of the mechanism itself, but then you set up the analysis in this option right here, and then select dynamic, because I want you to kind of understand and have this intuition that everything you change in the assembly includes these motors and these forces, because they're not part of the analysis. They're something that you use and you do the analysis with, but they're not part of the analysis. But now when we do set up the analysis, I can set this up to be dynamic, and we already have our motors selected right there. But now we have another option called external loads, and here we're going to apply gravity. This is why this is the dynamic option, and it's fantastic. We enable gravity, and I'm going to change the frame rate back to 10, because dynamic analysis is calculated slow as it is. I don't want it to be even slower by having 100 frame count for 10 seconds and have 1000 frames calculated. So I'm just going to leave it at 10, and I'm going to hit OK, and I'm going to run it. And I'm going to overwrite the kinematic analysis that I have saved before. So understand this: if you name this analysis definition 1, it's going to replace the playback analysis definition 1 with the one you're running now. Unless you change the name, then it's fine. So it's calculating with the acceleration applied. It's going to take a fairly long amount of time. I'm going to have a sip of water. Still going. Larger the assembly, the longer it's going to take. It's a good thing we changed the frame count to 10 instead of 100. Otherwise, we would still be at second 1. Alright, almost done. Okay. So I can hit OK now. And now I can go to measure. And remember, we already have that measure set up. It doesn't change anything. I can edit this, and it's set to be position. It should essentially be the same when I display it, and it is. It's essentially the same thing. But now, let's change that to a velocity. We should still have essentially the same values. Apply, OK, measure, and we do. It's increasing constantly, if you remember. But now let's measure the connection reaction. That's something we can measure now because we ran dynamic analysis. Now I'm going to select a connection reaction and I'm going to select an axis. And understand this, you can only measure connection reactions at connections you have made. It sounds redundant, but wherever you've made, let's say, a pin connection or a slider connection, those are the places where you can actually measure analyses, or connection reactions. You can't measure a connection reaction at a random point. That's not allowed. So let's measure this graph, and let's look at this graph, and let's run the video. Or before we even run the video, it kind of makes sense already. It should be a positive negative reaction, because when we move this way, when we move the mechanism to the right, there should be a reaction force acting against it, and the same thing in the other direction. But now let's just run the animation as we're, and this is too high fidelity, I think, but let's run the animation as we're displaying the graph. I kind of want to try to show you the graph clearly. Let me make this graph bigger. Okay, let me do playback and let me hit play. Let me slow this down even more. Alright, so I guess here's another point I can already make. Since we changed the frame rate to 10, you can kind of see how it's kind of jumping to the positions, and it's not really as high quality as we would like it to be, is it? That's the reason why you would kind of increase the frame count to increase kind of the accuracy of the result. This is very choppy and it doesn't really look as smooth. Okay, it's displaying it again. Alright, there we go. So that's just the reaction force. But now let's try to think about this graph right here. This is the connection reaction at an axis, at this axis. We would expect the connection reaction to go up because we're applying an acceleration. And I want you to kind of think about that. Because the acceleration is applied, the force, the connection force or the reaction force is gonna increase because we have our speed increasing constantly. It's not something that's a static value. We have our speed going up constantly. If you remember the velocity graph, it constantly goes up. So the speed of the link rotating around that shaft is going up tremendously. And this is exactly what we would expect of something that acts like that. Connection reaction would eventually go up. And of course this would break eventually if it started rotating way too fast. But it's not going to do that in Creo, but that's something you would do in FEA. So that's the point of dynamic analysis. But let me show you the dynamic analysis, or I should let me change the measure to the axes. So before we measure the reaction for the slider connection, let me measure the reaction here. So it's going to show us the reaction between this and that. Okay. Select this. Alright, so again, it should make sense to you that because it's starting to speed up slowly, and it eventually does speed up. Let's look at this graph. So up until here, it's fairly tamed, but as the speed rises, the connection reaction value rises as well, and that should make sense to you. And also, if you are kind of intimidated by these gigantic numbers, understand that this is in pound mass per second squared. So if I go back and close this, let me just not save this, exit without saving, file, prepare. Let me change this to IPS. Now watch, right here, units manager, pound mass. But now if I change the value, the force value to pound force, we're gonna have something far more reasonable displayed. Let me set that, interpret one-to-one, close, close. Let me save this. Now since I've changed the units, it's gonna want me to run the analysis again. I'm gonna go back to mechanism. Again, we already have the setup. The setup's already there. I'm gonna just run it again, and we're gonna have to wait again for the analysis to be done. I should get another sip of water. Almost there. It's starting to slow down even more towards the end of it, because it's, I guess, increasing in the amount of calculations it has to do. Still going, still going. Still going. Okay, so we're finally done. Alright, so let's look at the measure again, and let's look at this value. So now we have actual, reasonable values displayed. Not really reasonable for the size of the assembly, but you get the point. As it's increasing in speed, the reaction forces are going up to 400, 500 pound force. So that's that. Since the last pound mass per second squared values were in kind of thousands, I just wanted to change that to show you that this is still kind of a reasonable measure. But that's the connection reaction. Let me just measure the slider again, just cause, just to show you. There we go. So the maximum is about 140 pounds of force. It's not really that much, but that should kind of show you how to do dynamic analysis. You should know how to do kinematic analysis now, and you can change a bunch of these things. But the next set of things we're going to do are mainly going to be concerned with this side of Creo, where we're going to be working with a mechanism a lot. We're not going to be working with assemblies as much. We're going to make assemblies, but the things we're going to try to get accustomed to are gears. So we have something called gear options, cam options, 3D contact, and belt connections. So these are separate set of values that are available, not values, but constraints that are available in mechanism, and we're going to mess around with those, and we're going to try to do kinematic dynamic analysis with those, and I'm going to do case studies involving these tools, and this is what to expect next. But this is it for now. You should have a solid introduction to kinematic and dynamic analysis, although I guess my English is not really good enough to kind of explain a few things. I hope that it still helped. And thanks for watching.